Swayam Prabha. Digital India. Educated India.
Welcome back. So today I would be actually talking about in continuation to my earlier lecture about silicon processing and the various non-conventional techniques which are available for processing silicon, particularly with the MEMS perspective. So let us just briefly review our previous lecture. In the last lecture we talked about and discussed some of the materials which are used for MEMS. MEMS as micro electromechanical systems, and basically one of the primary materials for MEMS, because the processing of MEMS actually is nothing but borrowed from the microelectronic industry. Therefore, MEMS is more suitable to processing with silicon. So, therefore, we studied some of the silicon manufacturing techniques using the Czochralski's growth method, where a crucible maintained at an inert atmosphere was rotated and a seed crystal was lowered into the crucible for getting a bowl, and this bowl would be a sort of directional growth of the fused 99.99% pure polycrystalline silicon, which would be there in that in the crucible, and you can basically do the post processing of this bowl to obtain wafers with good super finish on the surface, as well as various thicknesses, etc. So, we also did some thermal modeling of the Czochralski's growth method, wherein we talked about things like one dimensional heat transfer equation, and try to understand how much the heat flow would be from the liquid side of the crucible to the zone of fusion, and from the zone of fusion to the solid, and the net heat balance was equated to the way that mass is formulated and in terms of its bonds of formation of the solid phase. So, we also obtained an optimum pull rate based on this modeling, and also try to optimize based on indicators like point defects and thermal stress related dislocations. And so, then we actually refer to a different model of silicon manufacturing using float zone method. Finally, talked about glass, which is another very important material for MEMS, and then we just started with some MEMS fabrication strategies, particularly the surface and bulk micro machining. Surface micro machining again being an additive process, and where it can be deposited, I mean the layers of thin films can be deposited on the surface, and bulk micro machining can be a subtractive process, where you can remove material from the volume of the particular wafer for doing machining. Now, let us look at some of the alternate MEMS fabrication processes which are available, and for doing that I would like to highlight this etching technique, subtractive technique. So, what really etching? Etching is a is referred wet etching can be dry as well as wet, and let us first see what wet etching is. So, wet etching is really a process where solid materials can be immersed in a chemical solution, and the solution can displace atoms or molecules from the surface of this material because of certain chemistries and reaction. Okay. So, when you talk about wet etching in microelectronics, mostly etching processes are isotropic or homogeneous in nature, which meaning thereby that the etch rates would be independent of direction, and it would be homogeneous in all the directions, and it would also be independent of the crystalline orientation. So, let us say if you are trying to etch this surface of silicon, and you have made this etch protective layer on the surface, which is not amenable to the etching process, or in other words it does not corrode or etch out if you are using a certain etchant. So, this can form a sacrificial mask on the top of this surface, and it can expose the silicon material which is underneath it in this particular region. So, the etchant can go and eat away the material, and it can go and start etching in all the directions homogeneously, thus obtaining a hemispherical crater like this. What is also important is because there is a rate of etch in the lateral as well as the vertical direction. Lateral etch would actually let the silicon cut to a size more than what it is intended to by this sacrificial mask. So, this process of extra cutting is also known as undercutting. So, because of this under etching or undercutting effect, isotropic etching has drawbacks in designing lateral structures, and therefore, you will have to always assume an etching allowance for this kind of etching to take place. If the solution is very well stirred, there is no accumulation of material coming off from these surfaces, and you can have this kind of a homogeneous profile. However, if you do not etch or if you do not stir the solution well, the atoms which come out from the surface are not being able to dissolve properly in the etchant solution, thereby creating a situation where, because of this high density near one zone, there may be diffusional restrictions and the etchant may not be able to etch in a particular manner, whereas other materials which are etched from, let us say, these sides may be having a greater etch rate, resulting in a directional etch rate. So, in this particular case the lateral etch is much faster than the vertical etch because of the accumulation of materials coming out of the material of the silicon. So, that is what happens when the solution is not stirred. Okay. So, there these paradigms are kind of used off and on for describing wet etching. What is also important is something called an etch selective layer. So, for example, you saw this mask here, the mask does not get affected by the etchant itself, although whatever is underneath the mask gets affected. Okay. So, this is called an etch selective layer, which is not amenable to the particular etchant which is being used in this context. So, it is called the etch selective layer. Okay. So, if we look at a table of materials which are commonly used in MEMS or microelectronics fabrication, you have the silicon, silicon dioxide, silicon nitride, aluminum. These are some of the common materials. So, these etchant materials can be, for instance, a combination of hydrofluoric acid, nitric oxide or nitric acid and acetic acid, or for example, the etchant material can be a simple KOH solution or a combination of hydrofluoric acid and ammonia, so on and so forth. So, these etchants are amenable to removing materials by etching action, which are mentioned on the table on the left. Now, the table on the right, the column on the right is basically indicative of what these materials are selective to, which means that if you are using this etchant solution of HF, HNO3 and CH3COH, as you can see here, it can etch Si or silicon, or and it can stop whenever it faces a layer of SiO2. So, that is what selective or selectivity of the etch process means, and how selective the etchant is in terms of its stopping the etching action is what selective to would mean. So, here the bunch of materials on the extreme right column, which actually indicates what are the selective layers for the particular material and etchant combination that we are actually looking at here. So, that is all about sort of wet etching, and the selectivity can also be defined by the way that the etching performs while meeting this selective layer. For example, there are two illustrations here, case 1 and case 2, as can be seen in this particular example. So, here for example, the etch selective layer, which is this yellow layer between the green and the pink, the etchant is not very selective. So, it has low etch selectivity. Thus, even though there is a stopping yellow layer, the etchant goes and disturbs the green material and it crosses the etch selective layer, whereas in case 2, it is a high etch selectivity. So, we can see that the etchant is more or less homogenizing the surface, and it stops whenever it meets the etch selective layer. So, that is the advantage of etch selectivity. So, a high etch selectivity is definitely desirable for MEMS processes to maintain a control on the dimensions, because the dimensions itself are very small as well. So, let us now look at some of the common etchants for isotropic wet etching, and this we had actually mentioned before. So, you have the material to be etched, the etchants which are used, and what it is selective to, and this table has been well described before as well. So, just for the records, these are very important for realizing some of the basic MEMS processes which would require this kind of wet etching action on the top of silicon substrates. Etching can be wet or etching can be dry, as mentioned before. Dry etching is basically a technique where you use a certain corroding gaseous atmosphere to eat away parts of the material which you are etching. So, therefore, dry etching is again something which a gas phase causes a reaction with an atom or a molecule on a surface by adsorbing onto a free site, and then taking away or carrying away the atom or molecule out of the surface. So, that is what the dry etching processes are. If you look at the different dry etching processes, you have physical dry etching as number one, which utilizes just beams of ions, electrons or photons. Okay. And what we mean by that is that essentially these beams are high energy beams which would deliver energy and bombard their own constituents like ions or electrons or photons onto the surface, and that would result in the damage of the material surface. So, it would kick off the material which is rather placed on the surface and well bonded. So, there is an exchange of kinetic energy of these ions, and atoms come out from the substrate surface because of this kinetic energy delivered onto the substrate. The high beam energy evaporates sometimes the knocked out material, and we will actually study in great details the mechanics of removal of material when we talk about the electron beam machining or e beam machining. Some of the limitations that this process has, that it has a slow etch rate and it is not very selective, which means that it attacks everything that comes in its way, and it can actually damage the whole surface very rapidly, because of which there is nothing called an etch stop or a etch selective layer which you can use for this physical dry etching. Another very interesting effect here is basically the trench effects which is caused by reflected ions. So, this is illustrated here in this example, that if you have a pit of this nature, and let us say you have a e beam which is coming and hitting onto the surface and is trying to deliver some electrons. So, there is obviously a deflection or bombardment of the electrons which would actually go and strike the surfaces like this, okay, and the momentum is still not consumed properly, and some of these electrons would bounce back, and so they would actually create a rough surface which is also known as the trench effects by the reflected ions or reflected electrons. So, that is an obvious disadvantage of physical dry etching. The other technique that we have is a chemical dry etching, where we are using a chemical vapor and promulgating a reaction between the etchant gas that we are using and the surface material. So, the etchant gas would chemically attack the material that you need to remove, and basically the gaseous products are conditions for chemical dry etching, because deposition of reaction products will stop the etching process. So, you have to be very, very choosy about what gases you are using for the chemical dry etching phenomena, and chemical dry etching is actually highly isotropic in nature, and it is similar to the wet etching because there is no etch selectivity whatsoever. The material, the gas phase which comes and etches away the material, the substrate surface is really not very well directed. It is like a vapor atmosphere which is attacking a surface into question, and so therefore, it is very homogeneous and very isotropic in nature. So, that is about dry etching. So, then there are other techniques, and before going ahead I would just like to illustrate some of the recipes of the dry etchant gases, as you can see here. So, here you have, let us say, and this is as far as the chemical dry etching process goes. So, the materials again are all indicated on the very left column, and then there are these etchant gases recipes, like for example, boron tetrachloride and chlorine, or boron tetrachloride and carbon tetrafluoride, or BCl3 and CHF3. All these different combinations of gases are basically etchants, or they act as etchants for the material silicon, and then they are again selective to SiO2, because there is some degree of selectivity that you can use in chemical dry etching, although the process is not very well directed and it is very isotropic in nature. So, these are some of these the recipes which you can think of while etching silicon or silicon dioxide or nitride or any other material of importance for the MEMS point of view, and the column here shows what these recipes are selective to, meaning thereby that a presence of this would act as an etch stop, and the etch will stop because facing of such a surface. Another very interesting example of etching is this physical chemical etching, which is actually a combination of chemical gaseous environment with some degree of mechanical or physical movement of the gases, and this comes into existence because of a form of or a state of matter called the plasma. So, as you all know, plasmas are nothing but made up of ions and electrons with a certain level of density of these ions and electrons across the bulk of the material, although the bulk is otherwise uncharged because you have equal number of positive and negative charges, but then these exist as ions and they can be driven to a surface and they can be used for carrying all these etchant gases or gaseous environment. So, if you can create a plasma and then create a chemical gas environment, then the directionality of the etching can be very well maintained, and some of these processes are very important from MEMS point of view. For example, reactive ion etching is a process where you create a plasma, and the plasma is semi chemically reactive in nature. So, therefore, one aspect of the plasma is how the plasma comes and attacks the surface, and another aspect of the plasma is basically there is a chemical reaction on the surface which it attacks. So, therefore, the physical chemical etching referring to a plasma and a chemical reaction both taking place together. There are some other examples of these physical chemical etching, for example, anodic plasma etching, magnetically enhanced reactive ion etching, and we will do these different forms of plasmas in great details in a little bit later. Then the triode reactive ion etching, and then transmission coupled plasma etching. These are some of the processes which can be categorized as physical chemical etching processes. Let us now look at a very interesting example of the basic of how you can go small. And whenever we talk about carving or creating thin features and structures, almost always the term which comes to our mind is photolithography. So, what is lithography? Many of you may have earlier done photography in your school days as a hobby, and in a photography what happens really is that you have a photo film, and this film is actually used to project whatever is there on the film using a beam of light onto a photo paper, and then once the photo paper is exposed, the areas which are exposed on the photo paper has a chemical reaction because of interaction with the photons, and you can actually develop it or dissolve this portion in a chemical solvent, and it results in creation of black and white pixels on the surface. So, that is what photography typically is, and especially in the olden days when digital cameras were not there, that was the only modality which was used for developing or printing of the photographs. Lithography is an identical process, only difference here is that it can be used at the micron scale, and instead of visible light sometimes we use ultraviolet radiation, which is very sensitive to resists, and the photo paper in a photography is replaced in a photolithography by something called a resist. So, let us see what is lithography in details. So, it is definitely the most important technique for fabricating microstructures, and depending on the energy of the beam, lithography techniques are quite divided into photolithography, electron beam lithography, X-ray lithography, ion lithography, so on and so forth. As is obvious, if you use light waves for doing lithography, it falls within the domain of photolithography. If you increase the beam energy, it falls within the domain of E-beam lithography or X-ray lithography, and ion lithography. Ion lithography you can increase up to any extent by accelerating the ion using an external electric field. So, I would like to mention here that the higher is the wavelength of a particular beam, lower is the beam energy, and vice versa. So, a high energy beam is typically characteristic of a lower wavelength, and the low wavelength means that you can actually resolve at a better sensitivity. And so, if you go high on the scale, you have better resolution of the system. So, as we all know, the very famous equation of diffraction of resolution theta, the angular resolution theta is actually expressed as lambda by d. Lambda, of course, is the wavelength of the incident radiation, and d is the distance of the object from the telescopic eyepiece. So, basically, as you see here in this example or in this illustration, if the lambda goes down or the wavelength of light goes down, meaning by thereby that the wave concerned wave is a high energy wave, then obviously the angular resolution theta will also go down, which means that you can actually distinguish between two objects placed by a closer distance more appropriately or better, in a better manner. So, therefore, the resolution really depends on the wave energy, and so if you keep on pumping up the wave energy, the resolution thereby increases, meaning that you can be able to distinguish two objects by writing them together at a closer distance and be able to make independent objects out of them. So, the patterning process with photolithography is really limited to two-dimensional structures and features. It is actually called a 2.5D process because the thickness of the features are defined by the spin speeds of the resists that you spin on the surface, and you can use the XY 2D surface for doing the patterning in whatsoever manner you want. Therefore, you can only resolve at a two-dimensional level. So, this technique uses a photosensitive emulsion layer called resist, as I mentioned before. It transfers the desired pattern from the transparent mask to the substrate. So, if you look at how photolithography is placed, really there are three steps in which photolithography happens. One is the positioning process, where the lateral positioning of the mask and the substrate which is coated with the resist is made, adjusting the distance between the mask and the substrate. Then there is an exposure process, where the optical or X-ray exposure of the resist layer is made, thereby transferring the patterns from the mask surface to the resist layer by changing the properties of those exposed areas. And then, of course, there is the third step of development, where whatever, as just in photography, whatever has been imprinted onto the top of the resist from the mask can be removed by physically developing it into a etching solution, and whatever parts are exposed are either removed or they keep there, thereby formulating micro size features or vias, whatever is needed. So, if you look at photolithography in a step by step manner, really it is illustrated here as an example. So, you have a mask surface, as you can see here, this is the mask, okay, and this mask is actually made more or less using the power of ACAD or AutoCAD files, and they are printed on transparency or hard masks. And then there is a light source at the top here, what you can see. So, the light falls onto the mask and passes through the mask, and thereby whatever features on this mask are made for blocking the light would block those portions of the light, and whatever features are open, and light passes through them and falls onto the wafer, which is actually coated with the resist. So, wafer is coated with the photoresist, and thereby it creates the imprints onto the top of the wafer, which you can develop and which you can actually develop later to formulate the features. So, for making masks, you use typically an electron gun, and you focus it using deflection coils, magnetic deflection coils, and you can very finely scribe a film of chromium, a thick film of chromium made over a glass, and this we call as hard mask. In case the mask is soft, even that option is available. You can get a printed transparency mask where there is a Kodak Mylar film, which you can actually print at a high resolution of about 5000 dpi dots per inch using a photo plotter, and the power of the CAD can again be used for printing different features and structures on this soft mask. And instead of using the hard mask in a very complex, which is actually fabricated using a very complex e-beam or and scribing onto the surface, we use this soft mask, which can actually imprint or serve the same purpose. However, in case of a soft mask or a polymer mask, the main difference or the main disadvantage is that you cannot go to a very high resolution, because it is limited by the way that dots are printed to formulate the images onto the transparency mask. So, typically these are the processes that would be used for photolithography. You start with a silicon substrate and clean the substrate properly, sometimes using recipes like Pirhana or even AMD, acetone, methanol, DI water, and then after doing the substrate cleaning, you basically spin coat the resist, the photoresist, which is actually the polymer material which is photo exposable. Thereby you actually do a pre-bake, where whatever solvent was used for spinning the resist uniformly on the top of the wafer is evaporated, thereby solidifying the resist film on the surface. And then after doing this pre-bake, you do the exposure using the masking process of the photoresist, so that whatever windows have been made in the mask are kind of printed onto the resist. And then with this printed shapes, you can do a post exposure bake, where the resist is again baked at a certain temperature, so that the heat is acting as a catalyst there. The photo exposure process typically is either a cross bonding or a debonding process, and the bond initiation between the polymer matrix actually gets either enhanced because of heat, or sometimes bond breakage becomes enhanced because of heat. So, heat is a catalyst which acts to fasten the reaction and the way that the photoresist is developed or exposed. So, after doing this post exposure bake, you do the development of the resist by using a solution which is actually something which takes away the resist which is either exposed or unexposed, depending on the type of the resist that we are using. And then after developing, you do another step of bake here, that whatever is remaining on the surface of the wafer can get properly hardened and settled, and also the developer can get removed from different places of the wafer, and thereby you get a of a certain feature or a set of features or patterns onto the surface of the resist wafer. And then you can do various things, like you can etch using those patterns, or you can actually strip the photoresist later after depositing metal, so on and so forth. So, this is the whole complex process of photolithography. If you look at the types of lithography, there are typically 3 different types of lithography which exist, and it really depends on the relative orientation of the substrate with respect to the mask. Okay. So, there are 3 kinds, as I mentioned. One is contact lithography or contact printing, where the mask and the substrates are in very close proximity, almost touching each other. is proximity printing or proximity lithography, where they are actually close, but not that close, because there is a layer of about 20-30 microns of air which is spaced in between the mask and the substrate. And then we have projection lithography, which is actually used in the industry, as proximity and contact are typically laboratory processes. For high yield processes, there is always a disadvantage of resist coming in contact with the mask and going away. So, therefore, projection lithography is more or less used in the industry, where you have a mask at some distance from the wafer, which is again spin coated with the resist, and then expensive optics is used to guide the light, so that the diffraction effects can be minimized, and then whatever is projected from the mask, passing from the mask, is projected directly onto the resist film. So, in the first two techniques, again the mask is brought close to the substrate, as I have just indicated. Contact printing lets the mask even touch the photoresist layer. The resolution B on such a case depends on the wavelength lambda and the distance s between the mask and the resist layer, and B is expressed as 1.5 lambda times of s to the power of half. Again, lambda is the wavelength, s is the distance between the mask and the resist layer. So, I have a small problem designed for you guys to solve. So, let us say you have a resist layer at the bottom of a 5 micron deep channel and a 20 micron deep channel. So, there are two different illustrations. One, the channel is 5 micron deep, another the channel is 20 micron deep, and this is to be patterned using contact lithography, and the photoresist is exposed to UV light, which is about 400 nanometers in wavelength, and we want to compare the resolutions B of the bottom of the two channels. So, in one case S therefore equals 5 microns and the bottom of this deep channel, and let us call it S1, and in the other case S2, the distance at which lithography has to happen is about 20 microns, assuming that the contact of the mask is actually at the top of the channel and the channel is below the mask. Okay. So, that is what we are assuming here. So, therefore, you will have the resolutions B1 and B2 as basically S1 by S2 to the power of half from equation 1 here. Okay. And therefore, this really is 1/4 to the power of half or half. So, therefore, the resolution in case of the 5 micron channel is exactly half the resolution in case of the 20 micron channel, which is illustrated here. So, therefore, as you are seeing here, the resolution B1 in the case of the 5 micron deep channel is better in terms of resolution distances, right. So, B1 is half the distance of resolution of the 20 micron channel, meaning thereby that deeper the channel, the blurrier will be the images. Therefore, the resolution would accordingly change. So, shallower on the channels or lesser the channel depths, the distance by which you can resolve two objects is lesser in comparison to if the channels are deeper. So, that is what is contact lithography. Typically, you can have the projection lithography resolution equation expressed in a little different manner. It is given by this lambda s by 2 and a, where lambda again is the wavelength, s again is the distance of the object from the masking layer, and then Na is basically the numerical aperture of the imaging lens system. Mind you, in projection lithography, you have to use expensive optics for guiding the light, so that there is no diffraction effect, because it comes through typically very long distances from small windows. So, therefore, a projection lithography system would have a resolution B expressed by lambda s by twice the numerical aperture of such a system. So, typically there are two different kind of resists which exist, and this particular illustration here kind of shows what would be the role of the two different kind of resists. So, one is a positive tone resist and another is a negative tone resist. So, in a positive tone case, as you see here, you start with the silicon wafer and then you spin coat let us say a small layer of adhesion promoter, which sometimes sticks the resist onto the surface of the particular wafer, and then you spin coat a photoresist layer which is represented by this yellow color here, and then you selectively expose the photoresist by this masking strategy, so that you can have patterning of the resist in this particular manner, and so you develop away the unbonded portions. And so, in one case, which is the positive resist, actually the resist which is exposed gets debonded and it goes away. So, a positive resist is signified by making vias or trenches. So, that is what the positive side of the resist is. The negative resist is, on the other hand, a resist where wherever you are exposing, you basically cross bonding. So, therefore, it goes through the same cycles as you are seeing on the right side here. There is a adhesion promoter, there is a photoresist layer, there is a masking strategy which you have made, and then finally you are exposing selectively these portions, and wherever it gets exposed, the resist stays back because it gets kind of cross bonded, and so you can develop away the remaining areas. Okay, and so basically the features and structures are ones which are exposed. So, it is a completely different form of lithography. The masking would be different, everything else would be different. This is SU8, is not S1813. So, therefore, with these two types of resists, in one case you can actually get features and structures like vias inside the resist. That means, wherever it is exposed, it goes off on development, and on the other you have structures and features and micro features actually itself, where there is cross bonding, and wherever it is exposed, it stays back, the remaining portions go away. So, a combination of both these resists would play a major role in building up micro systems, as we will see in future lectures to come. So, that is about photolithography. Now, let us look at a little different field of MEMS, which is also called polymer MEMS. So, as we know that increasingly because of the application of MEMS to the biological side for bioremediation, diagnostics, clinical detection, polymers become very amenable materials, because they are friendly as such with the biological systems, and therefore, there is a huge initiative in the area of polymer MEMS, which automatically comes in because of this merger between the biological world and the microsystems engineering. So, what is polymer MEMS? Polymer MEMS is, of course, the application of polymers to build micro features and structures, and this is basically owing to the friendly nature of organic surfaces and interfaces to biological entities, as they can identify. Most of the biological entities themselves are organic in nature, so they can identify each other very well, and so they are very friendly with each other. So, their behavior could be absolutely normal if they meet surfaces or systems made up of polymers rather than inorganic materials. So, if you look at some of the materials and their properties, particularly talking about polymers. So, in addition to silicon, whatever polymers you are using must have this property of biocompatibility. It should be ideal for biomedical devices. The polymer should be transparent within the visible spectrum. It should be rapidly fabricated. So, the fabrication strategy should be very rapidly be able to develop. It should be photo definable, which means that you can actually expose it, and based on that you can define the features and structures in a manner, and then it can be chemically modifiable. So, these are some of the desirable properties that would be in polymer MEMS, that it has biocompatible, it is optically transparent, it has properties of rapid fabrication, it has photo definability, okay, and then chemical modifiability. And if you look at some of the choices that the polymeric systems offer with one or more of the properties indicated here, there are polydimethyl siloxane. Of course, it is one of the very fundamental materials used in the biomems domain. Then you have hydrogels. Hydrogels are very highly cross-linked network of polymers, which has the capacity of absorption of water or some other specific pH materials and expand to almost 4 or 5 times its own volume. So, that is how hydrogels are very, very important. PMMA, which is an e-beam resist, again polymethyl methacrylate, is a very, very useful MEMS material for purpose of micro nano work. And then of course, Teflon, which is again highly hydrophobic in nature, with a contact angle of around 120 degrees or so in the at room temperature. And then of course, some of the polymers like SU8, S1813, these are the classes of polymers known as resists. So, all these are some of the choices that polymers have to offer for with one or more of the properties that have been indicated here. And to exemplify a few polymers used in as on date available commercial MEMS platform, you can look at this chip, it is a immunochip from Aclara Technologies, or as a matter of fact this lab on chip from Caliper systems, which are actually commercially available, and they are totally made with optically transparent photo definable polymer material, and they find great use and great novelty for many biological diagnostics and detection modalities. So, let us look at now some of the fabrication strategies and methods which can be used with polymers, and we really classify these polymers as soft materials by virtue of their properties. It is they have a sort of softness in terms of strength when you consider these polymers. So, that is why they are called as soft materials, and the soft material domain also includes biological materials apart from polymers. And all these fabrication is has really started from Whiteside's group, which can be called the sort of founder of how to fabricate some of the polymer MEMS. And the domain of process which is used mostly for the fabrication of this soft material is also known as soft lithography, just because you are using soft polymers, and you have to use one step of lithography, which can be then used, the mold that you eventually create can be used many times to have the soft material again and again molded across that mold. So, you have one step lithography followed by soft material driven micro molding, which would result in features and structures at the micro scale, and you can prototype it very, very rapidly as well. So, some of the soft lithography techniques, of course, replication and molding is a major technique, again developed at Whiteside's laboratory. Micro contact printing, again micro molding in capillaries, micro transfer molding, solvent assisted molding, micro molding, and then these two processes, dip pen lithography and compression molding, which includes hot embossing or injection molding and inkjet printing. These are some of the methods which can be classified under the domain of polymer MEMS. Okay. So, soft lithography is a class of processes, compression molding is another class of processes, and then inkjet printing is the third class of processes. These are some examples of what can be done with polymer MEMS. For example, this is an illustration of how PDMS doped with a Fe2O3 particle can be used to make these high aspect ratio structures. So, these structures must be about close to 20-30 microns high and maybe about 2 microns in diameter, and these can be used as tentacles. Just because they have Fe2O3, there is a tendency of an external magnetic field to move them, and they can be used for pedaling action, which can move forward the organism which would have or possess these tentacles. So, similarly, this is an interesting example of what soft lithography can do. You can see this this replication of a natural surface using polydimethyl siloxane, and very high aspect ratio replication is possible because of the unique property of this polymer, which is actually liquid at room temperature, but it cross links and cross bonds once you heat it at a certain temperature. So, let us look into some of the details of these processes. So, the first process which comes to our mind is replication and molding process, which is actually illustrated in the schematic towards your right here. So, what happens is that you create a master mold, which is made up of silicon, glass, metal or SU8 resist. Using lithography, you can create this mold, and this mold has a sort of negative impression of whatever you would like to realize on the surface and micro features and microstructures. So, the mask is exactly the opposite, inverted or negative of what features you are wanting to obtain. So, once this mold is prepared, the mold is basically coated with some surface treatment is done with some layer of HMDS or some hydrophobic material, and after this coating is over, basically after this treatment of putting a mold release agent is over. So, this is a mold release agent that we are talking about. You pour PDMS, which is actually available as a liquid form, and it is a mixture of silicon matrix and a curing agent, and you mix it in a proper ratio of 10:1 or 5:1 by volume, and the curing agent basically ensures the cross bonding between the silicone rubber of the material. So, once you pour this polymer on the top of this mold, which already has been coated by a mold release agent, you heat cure this PDMS for about 60 degrees and about 1 hour, so that it gets finely cross bonded. The cross bonding reaction is again heat catalyzed. So, if you put it in the normal ambient room temperature, it can still get cross linked, but it would take a huge amount of time. So, in order to accelerate the process, you have to actually heat cure it. Apply heat is an equivalent of applying catalyst, and so it gets into a rubbery form, and then because the mold release agent is already there on the mold, the rubbery form can be withdrawn from the mold without any much problems, and then you can have the exact negative of the features which were there in the mold imprinted onto this PDMS. So, it is like a rubber stamp that you are making in this process, and then you have to be little careful because PDMS is a soft material. So, there are issues of aspect ratios where length and width can be very critical, which you have to. So, if it is a high aspect ratio, then there may be a tendency of these features to kind of stick to each other as you remove them from the mold. If it is a low aspect ratio, that means the the height is much lesser in comparison to the width. There is a problem of the PDMS sagging down by its weight, and then closure of the feature or structure can be achieved this way. So, therefore, you will have to be careful about these two phenomena, pairing and sagging, because of the soft nature of the PDMS material. But again, it is a very useful process where you can actually make a replica which can be having structures and features of the size range of about tens of microns onto the surface, and you can use it as a stamp. You can do a variety of other processes based on that, and it is one of the fundamental processes in soft lithography, this replication and molding technique. It is very easily doable in any laboratory with just a little bit of infrastructure.